My name is Valerie Stolp, and in this video I will be reporting my observations for Physics 2211 Lab 4 Oscillations. In this lab we are exploring the arc motion of a mass oscillating on a spring by considering the various forces at work on the system. We will be observing the kinetic and potential energy of the mass and predicting the motion using the fundamental principles of Newton's second law, the position function, in comparison with the energy principle. The objective was to track a mass's oscillating motion from a pre-recorded video and use Python GlowScript to stimulate and predict the mass's motion by including the spring and force of gravity acting on the mass and Newton's second law. In this lab, we are factoring in the energy principle to compare the magnitudes of several energies at work. I found that my observations and predictions were well aligned for the period of the oscillation and followed a sine-cosine-like curve, but the results did vary in the height of the peaks between the two models. I'll explore these results more further in the video. The principles used during this lab were the momentum principle and its relationship with the net force and velocity, as well as the conservation of energy principle, and knowledge of forces, which are spring and gravity in this lab. For my code, the mass was given. I used the x and y position of the mass from tracker as the initial position for the code. The mass started from rest, so the initial velocity was 0. To find Ks, which is the spring stiffness, we solved 4 pi squared times m divided by t squared, and used the spring constant given in the introductory lab video, which was 6.83 newtons per meter for the y position. Next, L0, or the relaxed length of the spring, was found by setting the magnitudes of the gravitational and spring forces equal and solving for L0. In this case, L0 was equal to 0.123 meters for the y position. Next, we need to define the energy principle involved in the system. These are the formulas for the kinetic, gravitational potential, and spring potential energies. To calculate the changes in these energies, we iteratively took the final minus the initial, and were able to project the effect these energies will have on the motion. The change in the total energy of the system is the sum of the changes in energy and is equal to 0. I will go into more detail onto why this is later in the video. We also need to consider the forces at work, the gravitational force and the spring force. The net force is the sum of all the forces acting on the mass. And as always, when exploring physics principles at work, we include Newton's second law and the position update function to predict the future motion of the mass. After the code is run, you can see the mass is oscillating. The graph here shows these energies. The blue line is the change in kinetic energy. The red line is the change in the spring potential energy. The green line is the change in gravitational potential energy. And the yellow line is the sum of the changes in all the system energies. The changes in the spring potential energy and the changes in the gravitational potential energy have roughly equal periods and with slightly different sizes, but they are in opposite phases. As one increases, the other decreases. The change in kinetic energy oscillates almost twice as fast as the potential energy changes, and the mass gains and loses kinetic energy as the curve goes from positive to negative. The change in the total energy of the system stays constant throughout the oscillations, so the energy principle is indeed satisfied. It is 0 because there is no energy transfer with the surroundings when the mass, spring, and the earth are the system, because the attachment point of the spring does no work. I also adjusted the code to graph the y motion of the observed data from tracker versus the predicted y motion from Python. As you can see from the graph, the motion is relatively in sync. The red line is that of the observed motion, and the blue line is the predicted motion. The slight discrepancies could be due to the fact that there are less data points for the observed position than there are for the predicted position. So it looks like the observed motion jumps ahead. Also, we did not consider the drag force in this code. In conclusion, I will address some discussion questions. I will start with the energy principle. In this lab, my Python code does satisfy the energy principle, and that energy is conserved because, as seen in the graph on the last slide, the total change in energy remains constant at 0 during the entire motion. Furthermore, both the spring and gravitational potential energy nearly balances each other out because as one increases, the other decreases. The kinetic energy also comes into play, as it is both positive and negative as it reaches different positions in the oscillation. To further analyze the model, I compared the calculated periods for the x motion and the y motion. The period for the x direction was calculated from using the equation for the period of a pendulum, and this value was 1.62 seconds. For the y direction, I used the period of a spring and found this value to be 1.52 seconds. I found the percent difference to be about 2.01%, a very small difference. This is likely due to the fact that the length L of the spring is not constant and changes throughout the oscillation, and tracker cannot precisely observe the motion at every point in the oscillation. Overall, I found that the model prediction and observed motion are very similar, thus supporting the energy principle. Thank you for watching.